This work? No, I think it's set to table one from here, but oh yeah, yeah. Oh, Nancy, what did you do?
No, it's fine. That works?
Yes. Okay, so I will keep this short because we have already lost a few minutes. Please welcome Bhavna Chaglani. She's a computer science PhD candidate at UMass Amherst and works in the last lab with Prashant Shenoy and Jeremy Gavison. And most of her focus is around audio sensing and wearables, and she does a lot of privacy work as well. I met her at Ubiquitous, and I think she had an interesting talk about, and she'll talk a little more about that anyway. But I think she's had a great success with internships, like industry internships in general. And she's worked across MSR, Dolby Labs, Samsung, Nokia, and the list keeps going. And this summer she'll be at Meta. So please join me in welcoming Bhavna. And yeah, let's begin the talk.
Thank you so much for the introduction. Thank you everyone for joining today. I'm really excited to present my work on privacy-aware ubiquitous sensing systems for healthy indoor environments. And let me know if you have any feedback.
You're recording, right?
Yeah. So air quality is vital for our health, well-being, and productivity. And there is a lot of work done in maintaining good outdoor air quality. But as humans spend most of their time indoors, more than 80% of our time, indoor air is even more important. And indoor air consists of particulate matter like dust, smoke, biological contaminants like bacteria, virus, chemical pollutants like volatile organic compounds, and other gases. Now, these biological contaminants, like bacteria or virus, can travel through air and cause airborne transmission, which is particularly concerning during flu or pandemic. I started my PhD during peak pandemic times, when all we were hearing about was how healthy air is vital and everyone should be receiving optimal amount of ventilation. And there were guidelines from WHO and CDC that everyone should receive an optimal amount of ventilation. But there was no way for us to know that. While smart buildings research have systems in place to optimize energy and comfort, a very important aspect of indoor air quality, which is the viral loads or the infectious agents that transmit through air, have often been neglected. There is, to some degree, people have looked at indoor air in terms of CO2, volatile organic compounds, but not biological contaminants or the infectious agents. While increasing ventilation is one option, which we did during pandemic. So during pandemic, we increased ventilation at all times. But that is not truly sustainable because it leads to higher energy consumption. So having learned our lesson from pandemic, there is a clear need for monitoring and preventing the risk of airborne transmission in indoor spaces. Estimating the risk of airborne transmission is particularly challenging because it requires information about multiple factors like ventilation, aerosol, occupancy, where the people are sitting, etc. So for existing approaches, if you want to sense ventilation, as we all know, ventilation is important because it replaces the contaminated air with the clean air. But if you want to sense ventilation, for example, if you want to know in this room what is the ventilation status, you need to take the duct out and place the sensor inside the vent, which is just cumbersome. Aerosols are the droplets that carry bacteria or virus from one person to another and cause disease transmission. But if you want to sense aerosol, there is currently no solution. For example, if we want to sense aerosol in this room, we don't have sensors in place. There are dedicated equipment, but they are designed for laboratory usage, which are bulky, expensive, and they typically work in a clean room kind of a setup, not in everyday environments. While people have used CO2 as a proxy for airborne risk or ventilation, it is to some degree, it's effective, but it's not an accurate or a real-time indicator of airborne transmission or airborne transmission risk. So as we can see that the existing solutions are expensive, inconvenient, or inaccurate. Through my research, I asked this question that can we explore the untapped potential of audio signals for sensing airborne risk? My research mainly looks at this question that can we use audio signals to sense the key indicators that determine airborne risk transmission? And first of all, why microphones? Because microphones are ubiquitous. So for example, we have so many microphones in this room right now. Our phones have microphones, our laptops have, this owl has, we are just surrounded by microphones. So they are ubiquitous and well accepted. And there is a rich literature on using audio signals for similar health and wellness and similar tangential applications, like people have used audio sensing for detecting coughing, for detecting occupancy, and voice health monitoring. So it's all good. Audio sensing is low cost, ubiquitous, easy to deploy, already infrastructure is already there. But if I want to deploy a microphone-based solution in an indoor environment, it raises privacy concerns because it can record private conversations, it can leak speaker identity or other sensitive information. So before deploying any microphone-based solution in indoor environments like buildings, offices, workspaces, we need to ensure privacy before deploying any of these solutions. So the key research question here is that how can we sense the airborne risk using audio signals while addressing its privacy concerns? So in my research, I take a privacy-first design approach in designing all these sensing systems, which brings me to my research vision. So my work senses these airborne risk parameters like ventilation, aerosol, occupancy, mask, presence of mask, in a way which is low cost, non-invasive, real-time, easy to deploy, and most importantly, privacy aware. By using audio signals and by sensing these parameters, we can not only empower users with actionable insights and informed decision making, we can also assist building management in maintaining standards. So the next time if you want to decide or pick a restaurant to eat, in addition to the reviews and ambience, you can also look at how well ventilated the space is or is the air clean or not, which is an information that should be accessible to everyone. Which brings me to my research statement that it is possible to use inexpensive sensing modalities like audio in a way which is privacy aware to sense key environmental parameters that affect individuals' health in real time. So there are a few common research themes in my work, like privacy, audio, and health. And to this end, I make the following. I will talk about these works. The first one is FlowSense, which is an audio-based non-intrusive ventilation monitoring solution. This work is published in Invert 2022. The next one is an audio-based aerosol sensing solution, which is published in Invert 2024. And the combination of these two systems is published in NSYS workshop. Next, I will talk about how to address the broader concerns around audio privacy, which is feature sense, which is currently under review. And lastly, I'll conclude by talking a little bit about how we can monitor crowded densities in indoor environments. So let's go deep into how we can sense ventilation using audio signals in indoor environments like this one. So currently, ventilation sensing has many challenges. First of all, less than 20% commercial buildings in the United States have building automation systems, which has already retrofitted sensors. So very less buildings have these sensors, and even if they do have these sensors, that information is not accessible to us. And it is very expensive to retrofit a building, the entire building with those sensors end to end. So the other alternative is you can buy a differential pressure sensor or a vane anemometer, but if you buy that one, you need to take the vent out, place the sensor inside the duct, which is just intrusive and difficult to deploy. So there's a need to develop a low-cost, easy to deploy, and non-intrusive ventilation sensing technique. So the key idea here is to make ventilation sensing ubiquitous. And the way we do that is, the idea is to listen to the faint noise of airflow coming from the vent. And that noise is low frequency noise, which we can detect and then use that to predict the rate of airflow or the status of vent. And microphones are everywhere, so that would make it low cost and ubiquitous. So most of the airflow noise lies in the low frequency region. And while most of the ambient noise or our human speech, it lies in the higher frequency region. So the idea is to separate the two and use the lower frequency region to detect the airflow. But in doing so, there are three challenges. So first of all, it is not as clearly separable. So we need to first ensure privacy, as discussed earlier, that before deploying any solution, we need to make sure that we preserve user privacy. The second challenge is that vent noises are very faint and they are prone to ambient noise interference. And the last one is that we need to make sure that it is robust to user and environment factors. So the first challenge is how do we preserve privacy while sensing rate of airflow. So as discussed earlier, airflow is a low frequency noise. So we pass the audio signal through a low pass filter. But what should be the cutoff frequency of the low pass filter? This is our spectrum of interest. Up to 500 Hertz is where the airflow noise lies. So if we pick a lower cutoff frequency, we'll get better privacy, but lesser accuracy because the model will not have enough information to understand the rate of airflow. If we pick a higher cutoff frequency, we might have better accuracy because now we have more information, but it also raises privacy concerns because we are now overlapping with the human speech region. So we do experiments to identify what should be the ideal cutoff frequency of this filter, which I'll show in the results later. The second challenge was removing ambient noise. So ambient noise is dominant in this case because vent noise is very faint. So we use a pre-processing and a post-processing algorithm to remove the effect of ambient noise. So the first one is silent period detection. So we only perform sensing during the periods of relative silence. So during human speech or like right now, there would be some natural gaps in my speech, which we can detect. So whenever there are periods of relative silence, we would only sense during that periods. And the second is a post-processing algorithm. This is based on the observation that airflow noise is constant, is consistent and continuous. So it won't vary too much. It is like schedule based. So in every building, typically from 9 to 5, it's constant. So since airflow noise is consistent and continuous, as you can see the black line here, while ambient noise is transient and intermittent. So for example, when I am speaking right now or you are typing, that noise is very transient and intermittent. So they can be easily separated. So once we have the airflow prediction, we pick the minimum persisting value out of a consecutive window of predictions. So let's say out of 10 predictions, we will pick the minimum persisting value and we report that as airflow, which is much more robust and removes the effect of ambient noise. So we pick the lowest repeating value out of consecutive predictions. So by combining all these components together, we have the FlowSense architecture, where we first sample the audio signals. We have two prototypes. One is an Arduino based, which uses an Arduino microphone, and the second is a smartphone applications. So we sample the audio signal, we sense only during silent periods, we pass it through an optimal low pass filter, and later we convert the signal into frequency domain, and we use the amplitude corresponding to the frequencies, and then we pass it through a classification model and a regression. The classification model tells us whether the vent is on or off. And the regression model tells us what is the rate of airflow. Is it low, medium, high? What is the rate of airflow? And after the regression model, we apply minimum persistent sensing, which we discussed earlier, to get an accurate airflow rate prediction, and which removes the effect of ambient noise. So as discussed, FlowSense prototype, we have two versions of the prototype. The first one is uses an Arduino-based microphone, while the second one uses a smartphone microphone. For ground truth, we use a rev.p wind sensors, which gives us airflow in meter per second. For our evaluation, we conducted experiments with different types of vents, different buildings, different smartphone models, different distances and orientations from the vents, and we did a user study for privacy evaluation. So first of all, here is the result of the comparing different ML models for classification and regression. We found that XGBoost gave us the best accuracy for predicting the rate of airflow, so we picked that model, and we get almost 99% classification accuracy with all the models for predicting vent status. The next one is the cutoff frequency evaluation. So here we can see that we tried different cutoff frequency, and as we increase the cutoff frequency, our test MSE decreases, which means we are getting better and better airflow rate prediction because model now has access to more information. But after 375 hertz, it kinds of saturates and then further increases because now ambient noise becomes dominant. So we picked 375 hertz as the cutoff frequency. We also did privacy evaluation for 375 hertz, which I'll talk about it in a few slides later. And overall, we experimented the system with different levels of ambient noise and different types of ambient noise, like people talking or office machines or digital noise, and different decibel levels. And we found that overall, the silent period detection and minimum persistent sensing, both algorithms combined, the pre-processing and the post-processing algorithm, improved the overall accuracy by 77%, which means they effectively remove the effect of ambient noise from the airflow prediction. For our privacy user study, we asked users to listen to the original audio and then the 375 hertz filtered audio. And we had 12 participants listening to all these audios, and no user was able to discern any speech from the filtered audio, while they were able to understand the correct transcriptions from the original audios. So we saw that FlowSense transforms smartphones and all the ambient microphones into real-time airflow sensors, thus empowering users and building management to assess ventilation adequacy in real time. And the proposed optimal filtering, silent period detection, and minimum persistent sensing effectively preserve privacy and also remove the effect of ambient noise. We can further explore how we can use this microphone-based sensing solution for detecting any faults in the HVAC systems or any faults in a particular vent. So this was FlowSense, and we saw how we can use audio signals to predict ventilation rate or airflow rate in real time. Next, we'll see how we can use audio signals to sense aerosol emissions from human activities. I will wait for any questions. So aerosols are the key indicators of airborne disease transmission. So right now when I'm speaking, there are these tiny droplets that are being emitted from my mouth, and the ones which are less than 5 micrometer can travel up to 1 or 2 meters and would stay in air for hours. So they can carry bacteria and virus and cause disease transmission. So sensing these aerosol concentration is very crucial to determine the risk of transmission. So the first option that we have is an aerosol sensor, which is very bulky and very expensive, like $15,000, and it's complex for everyday use. It is designed to be used in a laboratory setting because it requires butanol, requires a clean room environment. People have used CO2 and occupancy sensor as a proxy, but they are not accurate indicator of aerosol. So for example, CO2 does not change with me speaking or coughing, but aerosols do change with that. And it's also not a real-time indicator, and it needs optimal placement to function effectively. We develop a system that predicts aerosol emissions, which is low cost, accurate, and easy to deploy. The key idea here is that instead of directly sensing the aerosol, which are the particles or droplets coming from my mouth, we sense activities that contribute to aerosol emissions. So there's a lot of study in the chemistry the papers, and they study how different activities contribute to different aerosol emissions. So instead of directly sensing aerosol emissions, we would first sense the activity and type of activity and level of activity, and then use that to sense aerosols. And we would use audio sensing to sense the activities. So aerosol emission depends on two key factors. The first one is the type of activity. So for example, if we all sit quietly here right now, there would be very less aerosol emissions, like 1 or 2 particles per second. But if we all started talking, it would lead to higher aerosol emissions. Similarly, coughing would lead to even higher emissions, and similarly sneezing. So different activities contribute different aerosol emissions. So if we are in a space where a lot of people are talking, there is more risk of airborne transmission. The second important factor is activity level. So if I'm speaking slowly right now, there is less risk of airborne transmission. But if I start shouting or singing or laughing, there is higher risk of airborne transmission. And if as I increase the amplitude of my voice, the airborne risk transmission increases. And that is why during COVID, the super spreader events were concerts or those events where there were a lot of noise when people talking. So in designing AeroSense, we have three main components. The first one is we first detect the type of activity, like coughing, sneezing, speaking. So we detect the activity type. And then we detect the level of activity, like how loudly we are performing that activity. And the third one is that we then use all these factors and predict aerosols. So the first component is privacy-preserving activity recognition. So there is a lot of work done in audio-based activity recognition. People have done cough sensing, cough, sneeze, and all the respiratory activity sensing. We use similar approach. In order to make it privacy aware, we extract non-reconstructible audio features from raw audio, like time domain features, spectral features, linguistic, and some handcrafted features. And then we use all those features to detect the activities. As you can see, each activity has a unique temporal and spectral signature, which we can use to distinguish between the activities. Also, mask usage reduces aerosol emission by 60%. Depends on the type of mask, but it can reduce somewhere around 50 to 80%. So if I'm wearing a normal N95 mask, then the aerosol emission reduces by 60%. So it is important to detect whether the person is wearing mask or not to get a correct estimate of aerosol emission. And we observed that mask attenuates high frequency components. So we designed features that can detect this behavior. So for example, we used low to high ratio, like the ratio of low frequency amplitude and high frequency amplitude to detect the presence of mask, and more such features. We trained multiple classifiers on open source datasets, which have labeled activities like speaking, sneezing, coughing, and also mask, speaking with mask and without mask. So this was activity type recognition. Next thing that we need to detect is activity level, how loudly the person is performing the activity. So to detect the activity intensity, we first localize the sound source, like how far the person is speaking from our setup. So for that, we used 2 microphone arrays, and we have the direction of arrival information from both the arrays. Using that, we calculate the distance of the sound source from our setup. Once we have the distance to the sound source, we already have the received decibel level. We use this information to accurately predict the decibel level at the source, because we need to know how loudly the person is speaking. And using that, we were able to achieve good accuracy in predicting the decibel level at the source. So this was activity type, activity level, presence of mask. There are other factors like active sources, voice liveness. So for example, if a person is speaking on Zoom, we don't want to count their aerosol because they are not contributing to any aerosol emission or a risk of transmission here. So we also need to detect voice liveness. So there are other factors that we detect which I have not added in this presentation. But after combining all these factors, we trained a regression model to predict aerosols in a clean room setup and followed by an aerosol aggregation step. So as I said, for ground truth, we don't have aerosol in this room. So the ground truth can only be obtained in a clean room lab kind of a setting. So we train a regression model there using that ground truth, and then we deployed the model in real world settings.
Like if we go back to the previous slides, how did you set up the cameras? And then are like the person who's speaking and also the two other cameras, where it is, and
So that's not camera, that's like a microphone array,
oh sorry, yeah.
which can give you like the direction of arrival of the sound source. So the way we set up is like this. So we have two microphone arrays placed. Now let's say this person is talking. So we get direction of arrival at both microphone arrays, and then we use trigonometry to get the distance to the source. So we want to find this distance from our setup, how far the person is from our setup.
So what's the geometry of your arrays like?
So these two are placed 30 centimeters apart.
Yeah, but is each of them an individual array, or are they just two individual microphones?
No, each of them are two individual arrays. So they are circular microphone array, and each of them are capable, they can detect the direction of arrival. So each of them has like 6 microphones in them.
So my question is, and do you want to keep questions at the end, or? So why do you need two arrays? Like, because one of them can also do a direction of arrival, and because we already know the exact geometry of within the microphones, is one array not sufficient?
One array is sufficient for direction, but we need distance.
Oh, you need distance for triangle.
Does that answer your question?
Kind of. I think it's more clear to me now. But then, so are those people in the clean room or not? Like,
No. So I will show you the clean room pictures as well. But okay, so this is the clean room setup. So this is clean room. This is called clean room because on the ceiling there are HEPA filters with laminar flow. So if you go inside this clean room, the particle concentrate count is 0. So there are no particles inside this clean room. And so the way we sense aerosol is, this is the particle counter sensor. This has a duct attached to it, and I'm wearing a mask, and another end is attached to my mask, another duct end of the duct. And then I sit in the clean room, and when I'm speaking, then it detects only the particles coming from my mouth. Because otherwise it would detect particles from my shoes or particles from our surroundings. It has to be very controlled. So this is the clean room, but those people, they are not sitting in the clean room. So as I said, the ground, there's no way we can get the ground truth in a real world setting. So I train the model here in a clean room setting and then deploy it in in the real world, we only have ground truth for the activity type and activity level, but we don't have ground truth for the aerosol concentration, like particle per second ground truth. We don't have it for the clean room real world environment.
Yeah, gotcha. And then do you have like participant difference? For example, if I'm speaking versus like anyone else.
So for now, we only have like 2 people's data from the clean room, and we just extrapolated that in the real world setting. But this is something that we want to do. We want to collect data from different participants because studies have shown that, so for example, from male and female, the particle concentration is different, and age also affects the particle concentration, and also the vowel content in the speech. And there are multiple factors that would affect the vowel. Yeah.
And sorry,
No, go ahead.
So how large is your data set?
So for activity recognition, we are using open source data sets. So Google Audio Set, which has activities, and then mask data set. For the clean room, we have like 20 hours of data collected in the clean. Yeah. So this is the prototype, which has like 2 microphone arrays placed at a fixed distance apart, 30 centimeters. And they are connected to a Raspberry Pi, and we conducted evaluations in office rooms, classrooms, and conference rooms. So this one is the evaluation of the clean room setup, where this is the clean room and this is the sensor. And we also place the microphone inside the sensor to get the audio and simultaneous aerosol data. And we observed that we achieve a low MSE and high regression score for predicting aerosol in a clean room setup. So there was a good correlation between the amplitude of your speech and the aerosol prediction. And for detecting the activity type, we get an aggregate accuracy of 86.33% in detecting different activity types like speaking, sneezing, coughing, and we get 75% accuracy in detecting presence of mask. Also, we could detect aerosol emission for different loudness levels, and this is again the clean room study.
Just curious about the choice of metric. When you say accuracy, is it balanced across the classes, or is
Yes.
it more?
It is balanced across the classes. So the main takeaways from here is that we have a novel audio sensing based approach to predicting aerosols because we are indirectly sensing aerosol from human activities. And we demonstrated the effectiveness of this in real world and controlled environments. So since our solution is based on microphone arrays, we can augment smart home assistants, which already have microphone arrays, and deploy aerosol prediction capabilities in them. We can additionally provide this aerosol emission data to building management system so that they can automatically modulate ventilation based on the increasing risk. So for example, let's say all of us start shouting here, the ventilation should automatically go up. And further, we want to study the causality between audio and aerosols because there are more studies that, as I was saying, that the vowel content also determines the aerosol emission. And it would be interesting to see what audio features and how they are correlated with the aerosol emission from an individual. So this was AeroSense. Next, I'll talk about how do we address the general privacy concerns around audio sensing. So in FlowSense and AeroSense, we saw that we performed different types of feature engineering to ensure user privacy, but it was a very application-specific techniques to preserve privacy. So we asked this question that can we generalize these ideas to enable privacy-aware audio sensing for general purpose applications, like not just for FlowSense or AeroSense, but for more applications, like let's say you want to detect typing or like coughing or birds chirping. You want to do different types of sound classification. How do we address the general question of the macro question of audio privacy here? So let's say we want to detect coughing, or like there's a baby monitor, there's a car honking or driver behavior. There are all these activities that we want to detect in a privacy preserving way. So currently there are two main challenges in audio privacy that we try to address in this work. The first one is that if we do manual engineering or handcrafting of features for a specific application, it requires manual effort and also domain knowledge. So let's say I want to design an application to detect baby crying. So for that, I need to know what features are related to baby crying, and then which one of those are privacy preserving, and then I can deploy a system, a baby monitor that detects baby crying. But that required manual effort and someone to know that domain knowledge. The second is expanding privacy beyond speech. So the most existing works in the literature, they somehow try to eliminate or obfuscate speech. So they would detect speech segment and then they would remove that speech segment. Now there are two problems with this approach. First, the accuracy of their speech detection is not very good. So some speech segments still pass through. And the second challenge is that speech is not the only privacy sensitive information, right? Because I can infer so much about you based on your non-speech information, like based on your coughing, I can infer what is your health status. Based on your crying, I can infer your emotional status. There are so many things apart from speech that are present in audio signal. So we want to expand privacy beyond just speech. So in feature sense, we designed a generalizable privacy-aware audio feature library that prevents speaker leakage, and we also design metrics to evaluate that. So here are our three main contributions. First is we propose a library that gives you access to a list of generalizable privacy-aware features. And in this work, we particularly assess and prevent speaker-related privacy leakage, like speaker's age, gender, ethnicity. We prevent these attributes. And once you have access to the privacy-aware audio features, we design an adaptive task-aware feature selection algorithm, which can select a subset of feature for your application based on privacy, utility, and cost constraints, and based on the application constraints that you provide. So if you say that the task is a non-speech human sound and you give a latency constraint and in a privacy utility trade-off parameter, the algorithm can automatically come up with a subset of features that are ideal for that task. Yeah, so this is feature sense. This work is currently under review. Lastly, I will talk briefly about CrowdSense, which is something I'm currently working on. And crowded areas significantly increase the risk of airborne transmission, which is well known. If there is sudden crowd in this lobby, there is high risk of airborne transmission there. So how do we detect these crowded areas? So here I propose to use Wi-Fi based location sensing to detect crowded densities in indoor regions. So for example, in this campus, there is already a Wi-Fi infrastructure and the IT department is already recording the association and disassociation logs. So there is already that data available. So that infrastructure is available and it is scalable. So whenever you connect to a access point and whenever you disconnect with it, that data is already being recorded. So can we use that data and design a system that can detect, monitor crowded densities and predict crowded densities in real time? And we want the system to be privacy aware, event driven, which means it should, apart from spatial temporal modeling, it should also take into account semantic information or contextual information. And we wanted to work on real time, on edge, and it should be personalized. So for example, today, if I want to go to the dining to eat, based on my trajectory, it can show me what are the crowded regions and how I can avoid it. Or I can wear mask. So this is an ongoing work, and I'm addressing many research questions while in designing this system. First of all, my previous systems mainly have used audio-based sensing. So I'm looking at how Wi-Fi-based sensing can complement audio-based system, because our audio is ideal for like a room-level system, but Wi-Fi is great for like a bird's eye view of the entire building or a floor-level occupancy sensing. And what are the key spatial, temporal, and semantic factors that are influencing the crowd movements in indoor spaces? And how we can do real-time and personalized trajectory-based alerts for people, which will really help them. So for example, for immunocompromised individuals who want to know how they can avoid crowded regions in a day. And most importantly, we want to do it in a way which is privacy aware. And lastly, I'm looking at how we can train a foundational model using indoor mobility traces. So there is some work done in training foundational models or large models for outdoor mobility, but indoor mobility is something which has not been looked at yet. Which concludes my talk. And in this, we saw today that how we can enable healthier buildings by using ubiquitous sensing modalities like audio and Wi-Fi logs. And we design systems which are non-invasive, privacy aware, and can give you a real-time assessment of indoor airborne risk. My vision is to basically advance more audio-based novel sensing systems around health and safety applications, and also address their deployment concerns, like they should be robust and they should work in real time. That concludes my talk. Thank you so much for listening, and thanks for joining.
I have one weird question. Assuming you were on the job market, what is like you said, audio has a lot of problems that we can solve through novel sensing solutions. What are these practical challenges in present day systems that you think are a limitation and that can be solved in certain ways?
Around audio?
Yeah.
Okay, so first is privacy. So if like for deploying most of the audio-based sensing solutions, I think privacy is the major challenge, and ambient noise, and then also like range, because it's not very like you can only sense it at this room level. So you need more sensors if you want to do it on a larger scale, and like Like, give me an example of a system and then we can discuss that.
No, you said like the vision is to advance more sensing solutions using audio. So what is
Around
currently
health.
missing in the current landscape that
Right.
you might
So
be
around
looking
health
at?
and safety, I think the main things that are missing is privacy. So for example, it's easy for someone to deploy a cough sensing or system on or like on body sensing or ambient sensing using audio signals. But I think privacy is a limiting factor in their deployment, and also ambient noise, and also sensor movement or sensor not being present. So those are some of the challenges that we can avoid.
Do you see like the position of the sensor, for example, a smart glass collecting the same audio versus like a smart watch or a phone or something? Is there a way to still make sense out of the same data being collected from multiple devices, or like what's a way to make it more device agnostic? Do you have any thoughts on that?
So I think that depends on the application. For some applications, maybe head-worn wearables are better choice because they just can collect data from this region. For some applications, maybe this watch is a better choice for some. So depends on the application. But I think that there is work on how these wearable devices can collaborate, and with the foundational models, if we can fill a missing modality, we can also fill a missing wearable sensor in that sense. So we can maybe look at that.
Any other questions? Any other questions on Zoom?
Yes.
So, you mentioned, like in the future, probably you also want to focus on the development. So have you, deployed any of the, or like, what, like, are you thinking about it? Or have you thought about it, and what are the things that you particularly interested in?
So I did deploy the FlowSense mobile application, but so the problem with that is so in my building, like in UMass Amherst, if the vent geometry is same, it works across the building. So if we calibrate it on one vent and one type of smartphone, then it would work on that cluster of smartphones and for that building. But if I want to deploy it here, there is a calibration step involved. So I have the app and it works well there. So that is one thing. And the second thing that I have deployed is earbud-based cough sensing. And so that was part of my internship work. But yeah, these two are the closest to deployment. Other ones still need like some work before the deployment.
And this CrowdSense will already use deployed stuff.
Yeah, CrowdSense already uses data which is there. Like we have data for around last 20 years of Wi-Fi logs from our campus and last 5 years of Wi-Fi logs from SMU campus. So that's why we're thinking of foundation model, because we have a lot of data.
I guess just want to make sure that I understand it correctly. So you mentioned like privacy awareness. So I like from your talk, I can tell like one of the strategy is you just get the feature out of the audio
Yes.
data. Are there other stuff that you already considered, but maybe not a big deal, or what are the other stuff that you could do for preserve the privacy?
Yeah, so I think in the past, people have looked at in literature, there are three main techniques for actually four main techniques for privacy preserving. First is hardware level, where you eliminate the part of the signal at the hardware level. So you design hardware level filter, but if you don't do it at a hardware level, then there are three techniques. Either you do signal level, which means either you inject some noise in the signal, or you pass the signal through a filter, like a low pass filter or a high pass filter or a band pass filter, or you just do selective sampling. So let's say instead of sensing continuously, you sense like 10 times a second, or like 1 time a second, which is very low, which preserves privacy. Or you remove speech segments. So you detect speech segments or any sort of voice activity, and then you remove that activity. So those are all signal level techniques. And then there are feature level techniques that kind of what I look at, where you either have a list of features that you extract from audio, or you let the model pick some features from the signal based on preserving some attributes, or do some sort of adversarial training which picks some features. So that is like feature level techniques. And then there are model level techniques which are like federated learning, differential privacy in that domain, which provide theoretical guarantees but reduce usability of the signal up to a great extent. So there are the three main levels, and I mainly work on the feature level, but I usually compare my work with the signal level techniques.
Interesting talk. Thanks again. And
Thank you
with
so
that, we
much.
can conclude the talk. Thanks for people on Zoom for joining. You can turn off the recording.
Thanks.